Hi, everyone. Thank you for joining me from wherever you are, and I suppose whenever you are. I'm Caleb Marshall. I'm a PhD student at the University of British Columbia, and my research is currently supported by a Vanier Fellowship. I want to start my Hello World talk by just saying thank you to the organizers. It's a really great opportunity to get a chance to give kind of a holistic explanation of your work, your experience as a mathematician, and I suppose your experience in life in general. So I want to start talking a little bit about me. So I grew up in a small town called Marshfield, Missouri, and then later I moved to a small city nearby named Springfield, Missouri. And I actually studied mathematics and statistical psychology at Missouri State University, which is located in Springfield, Missouri. And I had a really great just team of people there that supported me, advisors, teachers, mentors. My supervisors in mathematics were Bill Bray and Stephen Sanger, but I also worked a lot with Shelby Kilmer. And then my supervisor in psychology was Dr. Aaron Buchanan. After this, I completed my master's in mathematics at UBC in 2021. My supervisors there are Izabella Łaba and Malabika Pramanik, both fantastic mathematicians and also fantastic supervisors. They got me through COVID and also managed to get me through my thesis that I was writing during COVID, as well as coursework and just dealing with all the things associated with a master's degree while also being in the pandemic. So just immensely grateful to them and the support that they've shown me at UBC. And then I'm currently still a PhD student in mathematics at UBC, and they're still my supervisors. So I really love being at UBC and really love my time at Missouri State University. And for this talk specifically, I actually went through my photo archives and found this picture of me, Stephen, and Malabika. This is from when Malabika visited Missouri State University, and I think 2018, that's what my photos archive says, at least. And I just want to say that, Malabika and Stephen were really gracious in organizing a kind of research experience, a visiting research experience at UBC for me as an undergrad that really shaped my experience and excitement for mathematics as a young person in their undergraduate degree. I just feel really lucky and privileged to have had that opportunity, as someone who grew up queer in the middle of nowhere in Missouri. Being given opportunities like that are the kind of things that really build confidence and really show you that you can make it by doing something that you really love, which for me is mathematics. So anyway, enough about the sentimentality. Let me talk to you a bit about my research. So I'm going to talk about two general problems. The first is from discrete geometry, it's patterns in discrete point sets. And the second is from harmonic analysis and a little bit of number theory, which is related to the Favard length problem. And then I'll talk a little bit about my teaching and my community activities as well. But let me dive into the discrete geometry. So this specific project is joint work with Dr. Shelby Kilmer and Dr. Stephen Sanger at Missouri State University. So today I want to discuss a little bit about the geometry of finite point sets. Specifically, I want to talk about patterns that appear in finite point sets, which are subsets of Euclidean space. Of course, anytime you say words like that, we're mathematicians, we like things to be rigorous. So we would like to specify what we mean by a pattern. And ideally, once we have specified a pattern, we want to convince ourselves that studying the occurrence of that pattern or how often it occurs is actually interesting, right? So the first and perhaps most natural and also very difficult problems from this area, which are famous, are the Erdős single distance problem and the Erdős distinct distance problem. So the idea behind this is supernatural. If you think about what's one of the most common things we try to study in Euclidean space, well, we try to study the distance between points. So given a finite point set, it would be really nice to know, for example, in problem 1, how often a single distance appears. What is the general expectation for that, right? What is the best thing we can hope for, the sharpest bounds? And then in 2, trying to figure out how many different distances can be created by a finite set of endpoints. These, it turns out, are very difficult problems. Problem 1, in fact, remains open, while problem 2 was resolved something like 60 or 70 years after its inception by Guth and Katz in 2010. Naturally, whenever you have a problem like this that's this difficult, it tends to kind of have offspring. It kind of gets into the water and the air that we all kind of breathe and drink mathematically. And so this problem that I worked on with Stephen and Shelby is a variation of this. So we replace the notion of distances with instead dot products. And the other thing that we introduce is what we call a chain of dot products. So I've given this definition here. I'm just going to read it. The idea, though, behind this is that we start with a tuple of real numbers. So rather than specifying one distance or trying to figure out all the possible distances that can happen, now we're specifying a list of real numbers. And then of course, we're also considering dot products. So what is a K-chain of this type? Well, it's a K plus 1 tuple of points such that for the J plus 1 and jth point, we always have this identity. So the idea is we always want the J plus 1 dotted with the jth point to give us alpha J. So a kind of classic example in R3, if you take the three kind of unit vectors, right? Clearly, these three vectors, E1, E2, and E3, are going to correspond to a chain of type 0, 0, right? Because E1 dotted with E2 is 0, E2 dotted with E3 is also 0. So that gives you an example of what we would call a two chain, right? Okay, or a hinge. Now, of course, there's a corresponding notion of for distances. So instead of the dot product, you just replace that with the distance between points. And some of the strongest known bounds are due to Paulson, Sanger, and Schaefer. And Stephen was aware of this work because Stephen is Stephen Sanger. So we were kind of thinking through this problem and like cooking it up at the same time that they were doing this research. So what we're able to do, we're able to give an upper bound on the number of K-chains that can appear. This is an upper bound of if we have a set of endpoints and we have a chain of length K, we get that the number of chains of this type that can appear is n to the 2, K plus 1 over 3. So this makes a lot of sense if you think about it. Of course, why does it make sense? I should explain that to you. Well, as the chain gets longer, the multiplicity, so the amount of kind of shifting around we can do of the points, grows in something like a polynomial of n, right? So the longer the K-chain gets, the more kind of degrees of freedom or wiggle room we have to kind of shift our points around and evaluate K-chains. And so we would kind of expect a bound like this. So that is polynomial on n, and the degree is determined by the length of the chain, K. An interesting thing about this result, which we noticed immediately, was that when K is 1 and 2, this actually matches the best known bound for single distances. So this would be like the Erdős the Erdős single distance problem, as well as the sharp bound for distance hinges. So this is a pair of 3 points where you have D1 and D2. So these match, these problems align. So of course that makes you ask, well, for the general K-chains of distances, are the K-chains of dot products going to align? And the answer is no. This was the kind of second somewhat negative result of our paper, was we were able to construct a set of endpoints for which there are at least this many instances of a K-chain, right? So n to the K plus 1 over 2. Why is this important? Well, Paulson, Sanger, and Schaefer originally gave an upper bound of something like n to the 2K over 5. So clearly as K grows large, n to the 2K over 5 is less than K over 2, right? So if you look at this, this says that there are more, it's possible to have more K-chains of dot products than you could ever have of distances. So this is an interesting result. And it has some justification because what we noticed in our project is that if you take any point A and you consider the kind of radial line from the origin, any point B such that A dot B is going to be equal to alpha is necessarily going to be on an orthogonal line with this kind of radial line A, where the actual distance from the origin is kind of determined by the value of the dot product. So here we have another example where if we had a point C in this diagram, A dot C would be equal to beta. Now, of course, what this is telling you that the information about dot products can be encoded in terms of lines. If you think about the information from distances, well, that information is going to be encoded in circles, right? So there's generally, when we change this kind of pattern, the actual geometry of this pattern is different in Euclidean space. And so this is kind of our justification for why the bound begins to kind of diverge. It's also one of the reasons why this problem is in some sense easier. It's more attackable than a distance problem because we have a really powerful incidence theorems for points and lines. So because for each A and E, these kind of radial lines are unique, well, we end up getting the set E and its associated dot products induce a set of lines, which we call the alpha lines. And then we can kind of compare the incidence of the set E with these alpha lines and the associated kind of places that the dot products can fall, or the places that points making specific dot products can fall in these lines. We can use point incidence theorems to give upper bounds on how often these kind of chains can happen. And so this is kind of, we applied this result of Simonetti and Trotter. It's a famous point line incidence theorem. And essentially this, if you notice that our upper bound for hinges is equal to 4/3, n to the 4/3. Well, why is that? Well, when n equals m, the upper bound provided by Simonetti-Trotter, which would be a distance hinge, is exactly n to the 2/3 dotted with n to the 2/3, which is n to the 4/3, right? So that was pretty immediate. What was left to do was a bit of combinatorics to figure out how to chop up the longer chains, and that's contained in our paper. So I won't go into that. But what I will point out is that if, in fact, having incidence theorems is exactly the kind of thing that makes a proof like this tick. So if you have some kind of separation condition, so in this, I'm not going to read through the actual statement, but what I'll point out to you if you want to go and read the paper is that if you have some control over how many points are on a d-1 hyperplane and how many points are, for example, on a d-2 hyperplane, then you can also furnish a bound on the dot product K chains. And clearly, the idea here is just to show you that why we have this divergence between distances and dot products, where somehow we're able to get these bounds that diverge and are also seemingly easier to prove. Why are they easier to prove? Well, they're easier to prove because we have incidence theorems. So in any situation where you have an incidence theorem like this or a separation incidence theorem, you're going to get a similar result. And that's contained in our paper. So I would encourage you to go look at that if you're interested, or feel free to send me an email. I'll have my email at the end of this presentation if you want to talk more about this. I'd love to talk to it about you. It's a really fun project for me to work on. Okay, so that concludes my project, my talk about discrete point sets. Bit of a mouthful. So I'm now going to transition to some of the work that I've done at UBC as a graduate student. My work at UBC, so far, the papers that I've published and the kind of main things that I've been kind of scratching my head over have been something called rational product sets. So what is a rational product set? Well, you start with these two subsets of the natural numbers. And when I say n, I should say this is actually n union with 0, but it's, finicky things. And we specify that the cardinality of these sets is bounded below by 2. And we have all these conditions like L, we define an L, which is the cardinality of A times the cardinality of B. And we assume that the maximum is bounded above by L minus 1. All of this probably seems a bit finicky, but once we get into some pictures, I hope it'll make a bit more sense. We then assign kind of a multi-scale digit set. So the first step of constructing this digit set, we multiply A by L inverse, and of course, B by L inverse. And then at step n plus 1, we just iterate. So what does this set AN look like? Well, in fact, it looks like elements A in, because of our restriction, 0, 1, such that the sum AJ over LJ, A is equal to AJ over LJ for AJs in the digit set. So this is kind of, I defined this inductively, but this gives you an idea of what the set would look like. These sets pop up a lot in the literature. I think one name for them is actually called ellipsephic sets. So I know that these have been studied by a lot of people. And the idea behind this is that, with these digit sets, which, this set AN cross BN, which we're going to take, is a subset of the unit square, 0, 1 squared. We can use this to kind of tag a collection of basic sets. So in this case, we take AN and BN to be the bottom left corner of some certain squares. And then we take the union of these sets. And we call this, this is going to be an approximation at a given scale, in this case, L to the minus n, of a compact and self-affine set. So a nice fractal set with all the properties that we like in R2. So, okay, let me actually tell you how you would do this, because all of this is a bit, maybe a bit ham-fisted. So let's suppose that in this situation, let me look what I did. Okay, yeah. So let's suppose that A is equal to 0, 2, and I think I did 5. Yeah, I did. Okay, and then we're going to take B to be equal to 1 and 5. Okay, all right, so what does this mean? Well, we have L is equal to the cardinality of A times the cardinality of B, which is 6. And we now, how do we decide where we're going to place our points? Well, when A is 0 and B is 1, we place a point here. When A is 0 and B is 5, we place a point here. This corresponds to 5 over 6 and 1 over 6, respectively, for our vertical values, and then of course 0 for our horizontal values. And then we're going to do the same thing for our A values. So when A is equal to 2 and when A is equal to 5. So when the horizontal value is equal to 2 over 6 and 5 over 6, and then we're just going to place a square in each one of these. So rather than drawing an ugly square, why don't I just provide a little bit of shading? So we're going to get each of these squares. And so at step n, capital N equal to 1, we have how many squares? The number of squares is equal to L to the N, which is just 6. And the side length is equal to L to the minus 1, which in this case is 1 over 6. You can just kind of stare at this picture for a second to verify that, if you want, just to kind of think about this. And so this would be an example of a scale 1. So delta is equal to L to the minus 1 approximation of this kind of self-defined fractal. And of course, if we want to go to scale 2, what do we do at scale n equals 2? Well, we repeat the process. We write this kind of similar lattice. So we have 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5, 6 subsquares in each piece. And then we just pick the exact same kind of, we pick the exact same squares as before in each of the component subsquares. So one thing to notice, this is a aggressively deterministic construction of a fractal, because the specification of choices at every scale is fixed from simply these digit sets. So as soon as I specify the value of my 2 digit sets, this is going to generate, in fact, a unique self-affine fractal. And that's all I need. This is all the information that goes into constructing them. And so naturally, things that you try to prove are going to center around the kind of structure of these digit sets, A and B. Okay, so for this project specifically, we are interested in something about the linear projections of fractals in R2. So one way that you can define this projection is by this map. So one way of rewriting this is the same as the vector x dotted with the unit vector u theta. And up to a rotation, this is the same as if you had the line which made angle theta. You look at x here and you project orthogonally onto this line up to a rotation. This is going to be, this map is essentially the same as that map. So that's why we choose to kind of write it in this way. And so estimation of measure of linear projections of a set gives information regarding its structure. What does that mean? Well, this is kind of the classical Besicovitch projection theorem. So I say Besicovitch, it's Besicovitch-Federer, but Federer proved it for dimensions larger than 2, and we're only going to be working in R2. So if A is an H1 measurable subset of R2, then A is purely one unrectifiable if and only if the projection of A is 0 for almost every theta in 0, 1. And one thing I should mention, this is actually quite important, is that all of these sets that we construct up here, we constructed before, so what we call the rational product Cantor sets, these are all sets such that the H1 measure of S infinity is in fact finite. So that's the first thing. And in fact, their dimension, S infinity, is exactly equal to 1. So we're in the situation where the Besicovitch projection theorem can be applied. And in fact, if you take this a step further, you can in fact show that these are all purely one unrectifiable sets. This actually comes from the restrictions we placed on the digit set earlier. So that's kind of why we have this. And okay, so the object that I'm very interested in is something called the Favard length. So because E is one unrectifiable, the pointwise behavior, we have this kind of uniform estimate, which says that almost everywhere, the projection is going to be 0. However, almost everywhere and pointwise are decidedly not the same thing. So one way that we can quantify the behavior of this kind of uniform behavior is by considering this kind of average of projections. So the Favard length of a compact set is defined in this way. So the Favard length is just an average. So 1 over pi, 0 to pi. We're averaging in the angular parameter of the projection. So in fact, the Besicovitch projection theorem, one way of rephrasing it is that E is going to be purely one and rectifiable if and only if its Favard length is equal to 0, right? The only way for your average to be equal to 0 is if almost everywhere you are equal to 0. The only situation in which that happens when the projection is AE equal to 0 is if, this is if and only if E is unrectifiable, purely one unrectifiable. Okay. Great. So it seems like we're done, right? Because things are either 0 or they're not. But in general, we would actually like to use this object, the Favard length, to kind of deepen our understanding of unrectifiability in general. So one very interesting thing we can study is we can ask ourselves, okay, given a neighborhood of a given unrectifiable set, what is the expectation of this Favard length operator, right? It makes sense to consider projections of arbitrary sets in R2. In particular, we can consider projections of neighborhoods of sets whose projections are 0. So in particular, for the rational product Cantor sets, we do have an estimate. So the estimate that we have is that given these iterates, script Sn, which remember again, that's our multi-scale digit sets, plus this kind of basic square of side length L to the minus n. Matzela was able to prove that the Favard length of this is bounded below by C to the n to the minus 1. So remember, in this case, the scale of this fractal, the side length is L to the minus n, so it's bounded below by something like log of 1 over L to the minus n. So I'm going to write this correctly, to the minus 1. That's actually the Matzela bound. That's a bit messy, so I'll just erase that and point out again that the idea of this, though, is that it's polynomial in the power of n, which means that it's going to be logarithmic essentially in the diameter of the set. So this was proven in the 90s, and it was proven using measure theory. So just by considering energy integrals. And much later, so about 25 years later, for the specific four-corner Cantor set. So what is the four-corner Cantor set? That's the product of the middle half Cantor set with itself, which is also obtained by choosing your initial digit sets to be equal to 0 and 3. So in this case, L is equal to 4. So in this very specific case, Bateman and Wahlberg were able to, sorry, there should be an E here. Bateman and Wahlberg were able to prove that this lower bound is actually larger than 1 over n. So asymptotically, it actually genuinely departs from this 1 over n bound. So there's at least one set that behaves, in some sense, has slower decay than this 1 over n bound, this general 1 over n bound proven by Matzela. And what this tells us, it says that we can still push for an estimate of the form, this is bounded above by like n to some power, anything as close as we want to 1 over n, but we can't just have an expected uniform bound for these rational product Cantor sets of 1 over n. And so this is quite interesting in terms of generating problems, because what it tells us that, this kind of measure theoretic approach in terms of energy integrals gives us this nice lower bound, but there's still more to be done because these can depart from that bound. So proving upper bounds becomes kind of a very hot commodity for these objects. So unfortunately, or maybe fortunately, it depends on how you look at it, I suppose. This is a really hard problem because we have to really analyze the structure of these sets carefully in order to obtain kind of Favard length estimates. And one of the ways that we can do that is by actually appealing to some algebra and some number theory. So in my work with Izabella, we were especially concerned with two kind of key objects. The first is something called the mask polynomial of a set of positive integers. So notice t, right, is a subset of the natural numbers, right? So t of x is just x to the t, where t is coming from this set of positive natural numbers. That's why this is going to end up being a polynomial in x. We also are considered with something called the cyclotomic polynomials. These are the unique monic irreducible polynomial whose roots are primitive s roots of unity. And so the last thing we use is a bit of notation, is given a subset of integers. Now notice, this is a subset of integers, right, that generates the mask polynomial t of x. We let s sub t be the set of s's such that the s cyclotomic polynomial divides t of x. So we get this kind of division scheme. So of course, I can write all of this, but it would be nice to see an example. So this is a subset of the positive integers, again, union with 0. And of course, so we have this masked polynomial, 0, 2, 9, 11, 18, 20. You'll notice those correspond to the exponents that we see appearing right on the right-hand side. And this looks like an arbitrary set of integers until you realize that I chose it in such a way that this factors as 1 plus x squared times 1 plus x to the 9 plus x to the 18, which, if you know a little bit about cyclotomic polynomials, is totally okay if you don't. I didn't know anything at all about them until I started working on this project and brushed up on my algebra. You'll know that this is the same as x to the 4 of x multiplied by, phi sub 4 of x times phi sub 27 of x. And so in particular, s sub a is equal to 4 and 27, because those are the two s's which are going to divide a of x. Now you might ask yourself, how do you know that it's only 4 and 27? Remember, these polynomials are irreducible. So there's definitely not going to be another one that divides these two. So that's all we got. That's all, folks. Okay, so really a formative result that inspired Izabella and I's work on this problem was another paper from 2014 by Bond, Łaba, and Wahlberg. So of course, Izabella was involved with this, so she was aware of it. And so in this paper, there's a size estimate on the sets A and B, the digit sets. And in this situation, we have that the Favard length does indeed obey an upper bound, which is essentially polynomial in n. So it's almost polynomial in n. Now, there's this interesting, you might say, okay, well, why did you introduce me to all of this business with the masked polynomials? Well, there's another statement in here, which is that if, in addition, all the roots of the masked polynomial of ax and bx are roots of unity, then you get an improvement. So you actually genuinely get this kind of polynomial decay, not almost polynomial decay. And so this, even though they phrase the result in terms of cardinality, this hints at the fact that there is something regarding roots of unity and cyclotomic divisibility going on in their result. And in fact, that is a critical component of their paper, and our paper as well, is this kind of cyclotomic factoring of masked polynomials for the digit sets A and B. So this cyclotomic factoring actually comes directly from the Bond, Łaba, Wahlberg paper. And one of the things that they identified is they realized that every masked polynomial A of x factors as 4 pieces, and it's a product of irreducible factors. So there are these two cyclotomic factors. There is this kind of third factor, the product of irreducible factors of A of x that have at least one root of this form. And notice that this is an irrational, so it's not going to be cyclotomic polynomials. And then a part that has roots away from the unit circle. In particular, the piece that is quite a pain to deal with in terms of the Favard problem is this A2 piece. So this is the piece that Izabella and I focused on in our most recent paper and are still focusing on to this day. It is quite a spicy set of integers indeed. So what is this polynomial? Well, this is the product of the cyclotomic factors such that, of course, phi s is going to divide A, but we assume that s and L are co-prime integers. And as I said on this slide, I'll say it again, this is the main understanding the structure of this polynomial. This masked polynomial is really the main obstacle in proving upper bounds for the Favard length of more complex sets. So I'm actually going to, in the interest of time, I think I'm going to maybe skip this, but what I'll just point out is, this, when you first see it, I think you think to yourself, like, why, okay, this is a lot of number theory, and you're making me think about cyclotomic polynomials. Like, what the heck is going on? The idea behind this, though, is actually quite lovely, and I think it extends back really for decades on this study of something called Riesz products. And so the idea behind this is that when you have control of this kind of number theoretic business, you get something called an SLV set, or a set of large values. And essentially what this set has, it has two properties. Its measure is large enough for what we're doing, but also its difference set is contained in a set where a given polynomial is large. So this is a kind of, it's actually a kind of anti-concentration result for a given Riesz product. And so really, this is the kind of analytical bridge that connects the work that Izabella and I have been doing with the Favard problem, is this consideration of anti-concentration for Riesz polynomials. And I would really recommend reading the BLV paper, the Łaba paper, to understand more of this. It's a really lovely piece of mathematics and number theory. But the idea behind this is that essentially for this kind of product of bad masked polynomials, you want to essentially prove something like this, that there is a set such that the difference set is contained in this anti-concentrated region, and the set itself that generates the distance set has large enough measure. That's the idea. Okay, so great. What were Izabella and I able to prove? Well, if we set some kind of complexity threshold. So what do I mean by a complexity threshold? Well, we take this set of integers which parametrizes the bad cyclotomic factors. If we look at their least common multiple and we specify that the least common multiple is not too complicated, then we get a Favard estimate. So this is what this theorem in front of you says. So if SA and SB have at most two prime divisors each, so they're not necessarily the same prime divisors, they can have different prime divisors, then we get the identical conclusion of BLV. We get an almost polynomial decay of the Favard length of these certain neighborhoods of these very nice self-affine fractals. And of course, we also get the same, we can remove the almost polynomial business if we have that all the roots of AX and BX on the unit circle are roots of unity. So then we're good to go. So if we avoid the irrational factor that I kind of pointed out previously, we get the exact same result. Why is this important? I think if you read the Łaba paper, it is very clear that the study of the Favard length of rational product counter sets must be related to the study of the kind of number theoretic property of these Riesz products that they generate. So these kind of big products, which I glossed over a bit before. However, in their paper, this condition A and B, cardinalities being small, is indeed necessary to prove all these number theoretic statements, but it leaves you asking, well, is cardinality really the thing that matters for the Favard problem? And so what we're able to accomplish with this is by essentially refocusing and redefining what we mean by complexity. So in terms of complexity, it's in fact the complexity of these least common multiples of SA and SB that matter. So the more prime divisors these objects have, the more complex this kind of problem gets, and the harder it becomes to prove the kind of number theoretic statements that you need to prove in order to get Favard estimates. So, a bit about this would be nice to say. All that I would like to talk about it, but I'm realizing that I'm running a bit long, and I don't want to kind of drag through too much. But what I might just point out is that, in fact, the number theory that we have to employ is related to something called vanishing sums of roots of unity. There are really lovely structure theorems from the 2000s about these. One that motivated us was the Lam-Lung result on this. So it was a really foundational paper for all of this, including the Łaba work, which came before Izabella and I's work on the problem. But of course, these kind of results, since the cyclotomic polynomials are the polynomials that have these kind of roots of unity as their roots, they can be phrased in terms of cyclotomic divisibility. And so, in fact, what we did to kind of get the structure that we needed, the kind of structure results for these masked polynomials, is we improved a special case of the Lamb-Lung theorem. So the Lamb-Lung theory for the structure of vanishing sums of roots of unity is in fact sharp. There are counterexamples which sharpen their results. We're just in a very special situation where we have an additional hypothesis that allows us to get something better. So in particular, we're able to show that the masked polynomial has this kind of general lower bound. So one way you can think about this is we essentially prove that the A infinity bound is bounded below by something like this. And what is A1? Well, if you understand the definition of the masked polynomial, which again took me a while to understand, this A1 is in fact equal to the size of A. So you can go back to the definition and think about that a bit if you'd like, but this corresponds to proving under the hypothesis of certain cyclotomic divisors, we have a really nice bound on the size of A. So in other words, more phi m1 through phi mk dividing the masked polynomial of A of x implies that the size of A has to be larger relative to k. But this assumes that we have control of the complexity of these m1 through mk's, as I mentioned previously about the least common multiples, but only two prime divisors. Okay, all right, so I just want to point out before I leave this behind and talk about things that aren't my research that this was a really lovely project to be involved with. I learned a lot from it, and it's still ongoing. So the two prime divisor assumption is entirely an artifact of the proof that Izabella and I give. However, there's a lot of very difficult things that happen when you introduce more prime powers into this problem, and that's something that we're actively investigating, and I hope to be able to communicate more in the future is exactly what happens when we have more prime divisors. I also want to point out that the Favard length problem is a really, really lovely way to get involved with things like number theory, combinatorics, and projection theorems, as well as also probabilistic statements. So if that's something that you're interested in, I would love to hear from you, and I would love to, maybe chat a bit about this because it's a problem that's near and dear to me, and I've grown a lot from studying, and I would love to share with other people. So feel free to reach out if you have any questions about this, or if you have any ideas. I'd love to hear your thoughts on it. So anyway, thanks for listening to my research. I'm going to try and take 5 minutes just to wrap this up. I want to talk a bit about things in art research. So I was invited to join a certificate for advanced teaching and learning at UBC. This is a really cool program where it consists of essentially 3 pieces. So the first is that we have these kind of cohort meetings. So a bunch of us get together, a bunch of graduate students get together with some teaching faculty, and we're all from different, very diverse groups. So one of my best friends in this group is a dentist. Another person in the group is a zoologist that I'm close with. There's another person who's in linguistics. And we basically all get together and we talk about what is this crazy thing called teaching that we're all hoping to do as a part of our career. And a lot of our conversations aren't just philosophical. They also center on things like inclusiveness, ethics, pedagogy, and just even just getting a job. So it's been a really great experience. The other 2 things I've gotten to do is I've gotten to do regular guest lectures. So I've gotten a chance to give lectures at actually the graduate level, which is super cool. I got to give a lecture in Josh Zoll's Harmonic Analysis 1 course, which was great. Got to teach some introductory real analysis, which was really nice. And the other thing is that there is a component that's actually scholarship of teaching and learning. So I'm going to be teaching a course on introductory ODEs over the summer as a head instructor for the course. And so I'm in the process of adapting the curriculum to a cohort which is mixed between essentially mathematics majors and also engineering majors, and trying to find ways to split kind of the materials that we use so that it ideally suits both of them, so that they're getting everything they need out of the course while also attending the same lectures. It's something I'm excited about and like to think about is, how our individual backgrounds, how can we kind of meet our students' individual backgrounds while also, keeping faithful to the fact that we were teaching mathematics. So that's something I'm excited about, and I'm going to be working with Patrick Wells at UBC on this over the summer. I also really fantastically have had the opportunity to organize the Harmonic Analysis and Fractal Geometry seminar along with Alexia Yavicoli, and we're co-organizers. And it's been just really awesome to welcome some members of the harmonic analysis and fractal geometry community. I will say, just shameless advertisement, we're always looking for presenters, especially early career researchers, postdocs, grad students. If you have plans to visit Vancouver, or you want to make plans to visit Vancouver, please contact me and we can set up a talk for you in our seminar. We would just love to hear from you and hear what you're working on. So please don't be shy, reach out and we'd love to hear from you. And lastly, I'd like to talk a little bit about the 2S LGBTQIA plus activism I did. I really care about our experiences as queer people in STEM and mathematics, and also in society as a whole. I think this is a really complex and challenging time for a lot of people, and especially queer people. And so in Springfield, one of the ways I worked on this was just trying to generally improve the lives of queer people in just society around me by talking about everything from my experience coming out, also talking about anti-convergent therapy laws and things like that. But coming to UBC and being in Vancouver, my experience changed a bit because I do feel a lot more comfortable here as an out gay man. And so instead, I try to kind of focus on this idea of, what does a queer experience look like in STEM? What does it actually mean for us to come with our queer experiences and our experiences in terms of, class and in terms of all of our different intersectional identities? What does that actually look like in our work and in our research and our collaborations and our teaching in our communities? So part of what I've done in this has been serving on EI panels and also trying to be contacts for graduate students and undergraduates who are oftentimes really trying to find a way to, make a path for themselves in mathematics. So it's something I really care about and I'm really passionate about. And so if you would ever like to talk about that with me or talk about projects we can do together, I have a couple in mind that I'm working on that I really like to share with you. And as always, if you have graduate students or undergraduate students, or if this is who you are, a grad student or undergrad who is interested in coming to Canada to research mathematics and have questions about EDI and things like that, I would love to talk to you about it. I'm always open to have emails and a Zoom call with someone about this. It's something I'm passionate about. And mathematics and getting to study mathematics changed my life. And I've had an immense amount of privilege, which have allowed me to get to this point. So I would just love to share that and be helpful in any way that I can. So please reach out. And last but not least, this is my partner, Dimitri. He's a financial analyst, and my sweet boy Booger, who's my rescue puppy who just turned 1. This is a picture of us on one of our hikes. So yeah, it's been a really great experience to, study mathematics, go on this adventure, but also have just the sweetest, most thoughtful person in the world to back me up. And I wouldn't be here where I am today if it wasn't for him. So I just couldn't end a presentation talking about my experience without mentioning Dimitri. And of course, Booger, who can be such a jerk, but is so cute. I mean, just look at that face. Just look at that boy. He's a really good dog. So anyway, thank you again so much for listening to my talk. And I look forward to potentially hearing from some of you. Just to point out, my email is C Marshall. Sorry, my pen is freezing. C Marshall at math.ubc.ca. And just feel free to reach out about any and all things that you saw in this talk. Thank you for taking time to listen to me. I know it was a bit long-winded, but I just wanted to try and give a kind of full picture of my experience in mathematics. And I look forward to meeting many of you and seeing some of you again in the future. Thanks again for listening. Bye-bye now.